All right, welcome. Today we're going to investigate a central paradox in one of chemical engineering's most essential tools. In a process that is all about temperature, why does the famous McCabe Thiele method seem to completely ignore it? Let's dive in.
So let's just get right to the heart of the matter. We all know distillation is driven by temperature. It's what creates the vapor, it's what drives the separation. So why on earth does the most famous graphical method for designing distillation columns, the McCabe Thiele diagram, not even have a temperature axis? What's going on here?
You see, the entire diagram, the whole construction, it lives exclusively in this world of mole fractions, the composition of the liquid versus the composition of the vapor. Now, this isn't some mistake or oversight, it's actually a brilliant, deliberate simplification, and it's the very thing that gives the method all of its power.
To really get why this works, we have to pull back the curtain on the one single powerful assumption that makes this whole graphical solution possible. So let's play detective for a minute and uncover the culprit.
And here it is. The entire method is built on one core idea: Constant Molar Overflow, or CMO for short. Just think of it as a perfect one-for-one trade. It assumes that for every single mole of vapor that condenses down onto a tray, 1 mole of liquid boils up. This keeps all the molar flow rates nice and constant within each section of the column.
Now, of course, for this perfect one-for-one trade to actually work in the real world, a few things have to be true. The components should have similar heats of vaporization, you can't have heat leaking out of the column, and a few other things. Now, for systems like benzene and toluene, which are pretty similar, this works surprisingly well. But for stuff that's really different, this assumption starts to become the main source of error.
And here's the big payoff from making that assumption. CMO basically lets us sidestep the messy energy balance. It lets us decouple the mass and energy equations, which means we can solve the entire problem just by looking at where the material is going. And that, right there, is the magic trick. That's why the operating lines on a McCabe Thiele diagram are perfectly straight.
Okay, so if we threw temperature out the window to make our lives easier, how do we get it back? I mean, we definitely need to know the temperature profile of the column. Well, it turns out it's still there, hiding in the data, and we can map it out.
You know, the thing is, the temperature wasn't ever really gone. It was just an implicit variable, hiding in plain sight. As this quote says, that familiar XY equilibrium curve is really just a 2D shadow of a 3D surface that includes temperature. Every single point on that curve is tied to a very specific temperature through the system's fundamental vapor-liquid equilibrium.
And the tool we use to find that hidden temperature is the TXY diagram. You can think of this plot as the source code for our equilibrium curve. Every point on our McCabe Thiele diagram corresponds to a unique temperature on this one, linking the composition of the liquid on a tray to the temperature of that tray.
So how do we actually do it? Well, it's a pretty straightforward step-by-step process. First, you do your normal McCabe Thiele analysis, stepping off the stages. This gives you the liquid composition on every single theoretical tray. Then, you just take each of those compositions, find it on your TXY diagram, go up to the bubble point curve, and read the temperature right off the axis. You do that for every stage, and bam, you got your temperature profile.
But of course, the real world is almost never that simple. So what happens when our elegant simplification, that core assumption of constant molar overflow, just doesn't hold up? Well, that's when the plot thickens.
Think about a really common industrial separation, like ethanol and water. Their heats of vaporization are worlds apart. In cases like this, the CMO assumption completely breaks down. And when that happens, those nice, predictable, straight operating lines, they become curved. Our simple graphical method starts to fail, and we need to bring in some bigger guns.
And this naturally leads us to, well, kind of a ladder of different distillation models. Each model on the next rung up strips away an assumption from the one before it, adding another layer of rigor, and usually a whole lot more accuracy.
So, stepping up one rung on that ladder, we get to the Ponchon-Savarit method. This is another graphical technique, but instead of ignoring the energy balance, it tackles it head-on by using an enthalpy concentration diagram. This allows it to solve the mass and energy balances together for each stage, which means it doesn't need to assume CMO at all.
But let's be real. Today, the absolute gold standard is using process simulators. These incredible programs solve what we call the M-esh equations for every single tray simultaneously. That's M for material balances, E for equilibrium relationships, S for summation constraints, and H for heat balances. It is, without a doubt, the pinnacle of accuracy.
This table really lays it all out perfectly. You can see the trade-offs. It's not about which one is best, it's about using the right tool for the job. McCabe Thiele is just fantastic for building intuition and for initial designs. But for detailed engineering and optimization, you absolutely need the rigor of a full MES simulation.
So after all this theory, why does it matter? Well, because when you get out into the real world and you're actually running a distillation column, temperature, that one variable we started this whole journey by ignoring, it becomes the single most critical thing you monitor and control.
And this is true everywhere, from a massive oil refinery to a university organic chemistry lab. In that refinery, they use temperature as a quick and reliable proxy for composition, so they don't have to wait for slow, expensive lab results. And in the chem lab, you know that when the temperature holds steady, you're collecting a pure substance. The second it jumps, it's time to switch your flask.
You know, even that classic rule of thumb they teach you for a lab distillation, to adjust the heat so you get a nice slow drip of 1 to 2 drops per second, that's all about temperature. It's a hands-on practical way of controlling the temperature profile inside the column to make sure you're getting a good clean separation.
All right, so we've been on quite a journey here, from a simple graph to complex equations and all the way back to practical real-world control. So what is the final big takeaway from all of this?
Here's the most important thing to remember. The simple models never ever lose their value. The McCabe Thiele method is absolutely unmatched for building your intuition, for creating a mental framework of how distillation works. It's the thing that lets an experienced engineer look at a page of numbers from a complex simulator and do a gut check to know if the results even make sense.
And that leaves us with one last question to chew on, and it's a question that's really at the heart of all engineering. In a world where we have the computer power to model everything with incredible precision, how do we decide when good enough is actually good enough? If a simple model points you in the right direction, how much more rigor do you really need?